Okay, again, the idea is to use anything is same as e to the ln of a. So let's try to compute this by making it as limit of x going to infinity of e to the ln of this entire thing, 1 plus 2 over x, 3x.
But wouldn't the 3x jump down?
Yeah, well, by what rule?
The log, the frog log?
Frog over the log. Why is that hard?
I think you just introduced it to me. I can't memorize it quick.
Yeah. Not log over the frog. Frog over the log. Frog jumps over the log and comes down here. So it's going to be limit x going to infinity of e times 3x times ln of 1 plus 2 over x. Now the problem with this, huh?
I said I love the frog going over the log.
Yeah. The problem with this is that it's not a fraction. And we're doing all this to make something that looks like a fraction because we want to use the L'Hopital's, right? So what should we do?
Like it.
Could we set 1 equal to 2 over x?
Okay, well, there are two ways to go about this. One is to set x as 1 over t. Actually, that'll be easier. Because if x is replaced by 1 over t, then 1 over x will be t, right? If you flip both sides. There's 1 plus 2t, and then this will be 3 over t. So it will be a fraction. But then since x goes to infinity, t would go to 0 plus, right? So that's like one way to do it, which, by the way, is the easier way. But let's say we didn't know that. This is like a slick trick that if you know, you can save a lot of time. But if we didn't know that, what we can do is we can force it to be a fraction by making multiplication a division. How do you do that? Multiplication is the same as division?
Multiply by a fraction?
Yeah, you divide by a fraction, right? So you think of it as ln of 1 plus 2 over x divided by 1 over 3x. If you divide by the reciprocal, that's same as multiplication by a fraction. Okay, now let's see what this looks like. If you plug in infinity, then you get ln of 1, right? What's ln of 1? 0, because this is like log base e, 1 is e to the 0th power, right? And then if you have 1 over 3x and then you plug in infinity into x, what's this? What's this?
0.
0, right? So this now here is what type?
0 over 0.
0 over 0 type.
Wait, how is it ln1?
Oh, when you plug in infinity, 2 over infinity is 0, right? So you just have ln of 1. That's why in the numerator you have ln of 1, which is 0. Denominator is 0, so it's 0 over 0 type. Okay, why do we mention that?
No.
Because now we can use L'Hopital's. If it's 0 over 0 or infinity, you can use L'Hopital's. So let's use the L'Hopital's. Limit x going to infinity of, you differentiate the top, 1 over 1 plus 2 over x, and then the chain rule says you have to differentiate this and put it here. Derivative of 1 is 0, but derivative of 2 over x is negative 2 over x squared. Whether you use the power rule or use quotient rule, you get that. But then this is over the derivative of 1 over 3x, which differentiates to negative 1 over 3x squared. Yeah, so maybe this is easier. You can show this by using the power rule and comes up often, so you might as well just remember it. Okay, now what you can do is you can do keep, change, flip. So keep the top and change the division into multiplication, and you flip this over. So that's going to be limit x going to infinity of e to the 1 over 1 plus 2 over x times negative 2 over x squared times negative 3x squared over 1. So these cancel. Negative 2 times negative 3 is positive 6. So you get limit x going to infinity of e to the 6 over 1 plus 2 over x. And now it's clear, right? If you plug in infinity here, what is 2 over infinity? This will be 0. You still have a 1, so you end up with e to the 6 over 1, which is e to the 6th power. That's the answer. The answer is e to the 6th power. Now, I can't do the other case because I don't have time, but please try this. This is a lot easier to differentiate. Yes?
If it's 1 plus 2 over x, and
Yeah.
you plug it infinity for x, how would that equal to 1? Oh, because 1 plus 0 came out.
Okay?